In the first part of your lesson today, we're going to have a review of exponents. Exponents is a shortcut way to write multiplication of the same number. In a typical exponent problem, there are going to be two parts, all right? Two parts in your exponential notation. So in this example here, this is read as 5 to the third power. The 5 is called the base. Okay, and the base is what is used as a factor in the repeated multiplication. The 3 is called the exponent. Okay, and so when we look at 5 to the third power, again, that's an exponential form. What we would do with that is expand it. And so this would mean 5 times 5 times 5. It's the base being used as a factor in repeated multiplication. We used it 3 times because that was our exponent. And then when we evaluate the expanded form, we actually go ahead and do the multiplication. 5 times 5 is 25. 25 times 5 is 125. And so in examples 1 through 4, we're going to write each of the following using exponents. In the first example, I have the number 4 multiplied 3 times in a row, so it's going to be a base of 4 with an exponent of 3. In example 2, my repeated factor is x, all right, and there are 1, 2, 3, 4, 5, 6 of them, so that's going to be x to the 6th power. In example 3, 3 is the repeated factor, and there are 4 of them, so we're going to have 3 to the 4th power. And now in the last one, now notice that my two repeaters are different. I have x's that repeat, and I have n's that repeat, so I'm going to actually have two different exponents here. I'm first going to have x to the 2nd power, and then that's going to be multiplying n to the 3rd power. Now, when we multiply exponents, for example, 2 to the 4th power times 2 to the 3rd power, it's helpful to write out the expression, expand the expression. So I have 2 to the 4th power, which is 2 times 2 times 2 times 2. And now I'm going to multiply that by 2 to the 3rd power, which is 2 times 2 times 2. Okay, well that's just the same as doing 2 to the 7th power. And so if you were to do this multiplication, 2 times 2 times 2 times 2 times 2 times 2 times 2, you get an answer of 128. 5 times 5 to the 3rd power is 5 times 5 times 5 times 5, which is really just the same as 5 to the 4th power. And when I go ahead and evaluate that, I get an answer of 625. N to the 4th is n times n times n times n, times n squared, which is n times n. So my base of n was used 6 times in repeated multiplication. I can't evaluate that because I don't know what the value of n is, so I'm just going to keep it in exponential form, n to the 6th power. And with the last example, I have 7 squared times 3 to the 5th power. So I'm going to have my 7 squared, 7 times 7, multiplied by 3 to the 5th power, 3 times 3 times 3 times 3 times 3. And when I multiply all of that together, I get a final answer of 11,907. And so the rule that we can observe by looking at this when I expand my exponents, 2 to the 4th times 2 to the 3rd, was the same as 2 to the 7th. 5, well that's the same as 5 to the 1st power times 5 to the 3rd is 5 to the 4th power. N to the 4th power times n to the 2nd power was n to the 6th power. So if I have two bases, okay, that are the same, and I'm multiplying them together, all right, base of a, exponent of x, exponent of y, I can rewrite that as the same base, and I'm just going to add the exponents together, a to the x plus y power. All right, 2 to the 4th times 2 to the 3rd was 2 to the 7th, 4 plus 3 is 7. 5 to the 1st times 5 to the 3rd, 5 is 5 to the 4th power, 1 plus 3 is 4, etc. So if your base is the same, you can add the exponents if this is a multiplication. If we're dividing with exponents, again, it's helpful to write out the expression in expanded form. So I first have 2 to the 8th power, so 2 times 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 2, all over 2 to the 3rd power, which is 2 times 2 times 2. Okay, and this is especially helpful to write it this way because I notice that in the numerators and the denominators, I have factors of 2 that I can simplify. 2 in the numerator cancels with 2 in the denominator, another 2, another 2 in the numerator, another 2 in the denominator, and so I don't have anything left in the denominator. I can think of that as the value of 1. But in the numerator, I still have 5 copies of the number 2. So this is really just the problem 2 to the 5th power that I'm doing. And when I evaluate 2 to the 5th power, it gives me an answer of 32. 3 to the 5th power is 3 times 3 times 3 times 3 times 3. 3 squared is 3 times 3. And again, I have 3's in the numerators and the denominators that I can simplify with each other. And so that just leaves us with 3 to the 3rd power. 3 to the 3rd power has a value of 27. N to the 9th divided by n to the 7th, so let's go ahead and expand those. N to the 9th, 1, 2, 3, 4, 5, 6, 7, 8, 9 of those, divided by n to the 7th. 1, 2, 3, 4, 5, 6, 7. And now I can do my simplifying. So I have 7 n's in the denominator that I can simplify with 7 n's in the numerator. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That leaves us with n to the 2nd power. And again, we can't evaluate that because we don't know what the value of n is. All right, and with the last one, I have 2 to the 4th divided by 5 to the 6th. 2 times 2 times 2 times 2. Divided by 5 times 5 times 5 times 5 times 5 times 5. Now notice this time that my numbers are different. 2's and 5's don't simplify with each other, so I'm just going to go ahead and evaluate this. All right, well, 2 to the 4th power in my numerator is 16. 5 to the 6th power in my denominator is 15,625. Okay, and so looking at this example, when I have the same base and I'm doing a division with exponents, 2 to the 8th divided by 2 to the 3rd left me with 2 to the 5th. Well, 8 minus 3 gives me the 5. 3 to the 5th divided by 3 to the 2nd was 3 to the 3rd. 5 minus 2 is 3. So if I have two bases that are the same, and I'm dividing, so a to the x power divided by a to the y power, I can keep my base the same, and I can rewrite the exponent by subtracting those exponents, x minus y. The next section just gives some useful rules to remember when dealing with exponents. If I have an exponent of 0, any number raised to the 0 power is going to be equal to 1 unless that number is 0. 0 to the 0 power is undefined. So 4 to the 0 power is 1, 2500 to the 0 power is 1. Any number except for 0 raised to the 0 power is going to be equal to 1. If you have a negative exponents indicate reciprocation, with the exponent of the reciprocal becoming positive. All right, so for example, if I have 3 to the negative 2nd power, that's the same as 1 over 3 to the positive 2nd power. All right, 1 over 4 to the negative 3rd power just becomes 4 to the 3rd power. So it indicates a reciprocal if you have a negative exponent. Another helpful rule to remember is the power to a power rule. If you raise a power to a power, you keep the base and you multiply the exponents. So I have 2 squared. That value is being raised to the 3rd power. So I can keep my base of 2, and I'm going to multiply those two together. That's going to give me 2 to the 6th power. On the back, we have some practice examples. Evaluate if possible. We're first going to rewrite them with a different exponent. Okay, so we're going to use our exponent rules that we've been studying, and then we're going to evaluate them if possible. So I'm going to give you some select ones here that I want you to try to rewrite with a different exponent and then evaluate if possible.